Hello, gentle readers. Today is March 19th, 2024. From a desk with Ross Finlayson, in a study of foundations, is moment in motion. Acceleration. Where does it start? Where does it end? How does it commence? How does it complete? These are the ideas I'd like to try and figure out today. Because in physics, we have what's called the laws of physics. So the laws are what is in motion stays in motion, what is at rest stays at rest. And two objects, what collide, make an equal and opposite reaction. So that's it. Then, of course, that's kind of facile because we're just talking about kinetics plainly. And exactly what was in the kinetic energy of the thing, and how they're apart and connected, and vis-a-vis their interactions and interference, and otherwise their orbits is all about each other according to gravity. Somehow there's this force of gravity that's one of these other laws. It's not just a good idea. And so what I've been trying to think about, and it developed quite a bit in this descriptive differential dynamics bit, and is forming as one of these ideas, is that the higher orders of acceleration. So when we think of velocity, it's the change in position over time. And then with regards to the rest, there's no change in position over time. So are these first two laws the same? Motion, motion, rest, rest. Kind of the same, except the one at rest indicates this like it must have something to make it move, and the one in motion says it must have something to make it not move. So it's the same kind of stasis, the same kind of dynamic, but either way, one way or the other, these ways. Are there any really truly zero quantities or magnitudes? One avers that there is, yeah, because to go from positive to negative or this way to the other, it must cross, if not, and not jump such boundary. In a continuous world, here everything is assumed to be continuous in the sense that it's not really falsifiable to say that the world is continuous, but all the models kind of built to it in the continuum limit, so it kind of must be also that there's not just the discrete and the granular at the extremes, that we're living in a hologrammatic universe of a continuum that can all fit 3 dimensions in one, and then time falls as a ray out this way. The usual idea that objects in space make space contraction and move through the space, and then that gravity and the space relaxes as this force comes and goes, and then that's all entirely balanced out by the infall gradient of gravity through the whole universe as only the most utterly fine, according to the cosmological constant being a mathematical infinitesimal, gradient, and otherwise the isotropic universe, the universe as far as cosmology can find is not anisotropic. So the idea is then that this makes for a sort of overall Machian principle. Mach is for whom's named the speed of sound, or 770 miles per hour at sea level, who didn't discover it, but for whom it is named. That acceleration and the higher orders of acceleration here is the idea that I want to kind of understand a little bit better. So when we wonder how acceleration is defined in terms of physical quantities have mass. So mass is the amount. It is the conserved quantity, saying that as long as something is of a particular form, a state of matter called matter, and not energy and some of these other forms, with the equivalence principle that energy is the medium of exchange for these things, that it's conserved quantity. And so within an open or closed system, it affects that if it's open, it comes and goes, and if it's closed, it stays. So then that gets into, we have that for a body, it's defined by position and time, and for a massy body, it's defined by mass, position, and time. That is the body. The body is the mass, and the body is also the space that it's in. It's not exactly a point particle. What we have is kind of the point and the total. So that's like the most inner product, the most outer product. And then in the middle of the milieu is the local and the global, so the near field and far field. These are the point, and right between the point and the local is kind of the object. And that the between the local and global is the surrounds, and between the local and global and total then is the farther surrounds. Fine, okay. So then how is acceleration defined in terms of this? Well, force is mass times acceleration. So if you know one or the other of those, you solve for the other ones in terms of it. Or if you know one or the other of those, then the other ones are variables in terms of it. They're all variables in terms of each other. And it so results that this is the definition of the linear classical application of any source of change at an instant, what results any sort of change in velocity. So at any given instant, acceleration, if non-zero, if zero or non-zero, is constant. But how did it get there? So the idea is then to figure out how to understand the higher orders of acceleration. So this is variously called jerk, then snap, crackle, and pop. And with regards to that, there's position, velocity, acceleration, change of velocity per time, jerk or snap, crackle, pop. Over time, these terms have varied a little bit because it used to be kind of like one or the other, and then which one was next. These descriptive terms, all these higher orders of acceleration. And so then there's always generally considered to be change in acceleration, change in time, change in that, and change in time, change in that, and change in time, change in that, and change in time. From meters per second to meters per second infinity. So it's just kind of broken down piece by piece and bit by bit until all of those are non-zero, to generally reflect as like, well, first we just have the two laws that things stay the same, and then dynamics is any application of force at any instant. So the force must be a function of time to result the acceleration as a function of time, and then that has a formula with regards to then the body, with regards to its inertia and momentum, that being capturing the energy and that which has that it's moving, the momentum, in the space contraction overall, but in the Galilean only perfectly, classically, and exactly as where the billiards are geometric and always add up, these kinds of things. That then trying to figure out that those terms are defined in terms of each other, and their dimensional analysis gets into that, then momentum is just mass times velocity. Something is moving, and it will impart as much momentum as when it hits a theoretical brick wall as all of it. And the only equal and opposite reaction is one's movable and one's not movable. That's a full momentum. There's an immovable object vis-a-vis an unstoppable force. Right. So these are usual familiar concepts when starting to explore the ideas, and I haven't really thought of them for a long time, but the immovable object and the unstoppable force. What happens when they meet is also underdefined. What happens to make something that at rest go into motion or go into motion to rest, underdefined. See, these are the great things that can get into the ideas to help establish and explore moment in motion, the inertial moment, and the very idea of moment basically being entirely about the application of something turning around. That is the fixed in the frame, the singular, which just otherwise is changing its perspective, changing its geometry in the motion, right? So, mathematics and physics together make dimensional analysis. And so we have quantities that are numerical quantities, and then we have quantities that are physical quantities. So they have units. Units of the numbers, the modular, the integers, and all these kinds of things. Units of physical quantities, here for example, mass. Time and distance reflect these first dimension quantities. So here, in this classical model, mass is a first dimension quantities. It's to the 1th power. It's like so. Length naturally makes area, naturally makes volume in the dimensions as of its powers that are same as its algebraic powers of these units by these dimensions in the dimensional analysis, helping explain that 10 times the length of that's called the length 10 is in the one dimension, whereas 10 squared is that when you square the numerical side, you also square the units side, the physical unit side. It's dimensional analysis. Okay. So you got mass and length and time. And then you got distance. So are distance and length the same? Well, kind of, except it's one's of the body's position and the other one's the motion's distance. They have the same units. They're related after the derivation of the quantities. What to them are dimensionless quantities, where a dimensionless quantity is just the numerical value. It's got no units, right? Or it's got units above and units below that cancel and vanish. That this is how dimensional analysis makes for dimensional analysis, dimensionless quantities, derivations of quantities, which makes in our analysis and in our algebraic, that they're always associated with these implicit, all the quantities, all the units, none. This numerical quantity is like, I'm in whatever units are so prescribed, and all these other ones are zero. Vis-a-vis the finite and the classical and the impulse and what is at any one moment, just one of those. So velocity and acceleration are related to each other as by the derivative with respect to time and the antiderivative with respect to time. So if you take the change of velocity with respect to time, it's by definition the acceleration. And if you integrate the acceleration, you will see the change of velocity. The sum of that is like, well, was that just a quantity by itself? It's like, well, it gets added. It's like, well, doesn't that mean it kind of accumulates somehow? It's like, yeah, it sure does. But you just take the integral and it kind of works out? Yeah, exactly so. So the idea is that then the next higher order of acceleration is dA dt, change of acceleration for change in time. And then that gets up into the higher order, the higher order, the higher order, and dot, dot, dot. So at some point, and this is this gentlest push of the object from the very, very, very top of the toppling domino will start it in motion at all, at which time it gains acceleration in the well of gravity till it falls. And tipples or topples is about the middle. It's moment of inertia. Or it's about either end. Whether it's perfectly otherwise arranged, or whether it's connected and falls as like a hinge, whether it's hinged or unhinged. That quantity is essentially zero, yet it's then has the accumulating, because there's a constant field the other way that changes it from its astable configuration to a more stable configuration, an equilibrium. Everything is always in equilibria as it falls out of it. That's the way it is. So the idea is then that the change of acceleration with respect to time is a higher order acceleration, and then that's second derivative and its third derivative and its fourth derivative with respect to time are all these higher orders of acceleration, and then they're supposed to integrate over the time, over the space. See, we've already introduced kind of this difference between length and distance, though they're the same in units, about the dimensions they go through, the all of them or the none of them, right? Helping to explain why classical mechanics has a lot that's implicit and underdefined that kind of comes back into this as kind of thing. So all we have is like that the kinetic energy is 1/2 mv squared. So velocity is squared, and that's the energy overall. And it takes the same amount of energy to speed it up as slow it down. Vis-a-vis the momentum which gets exchanged in collisions, and then the orders of that and the instantaneous of that. Vis-a-vis the turning of things, vis-a-vis their perfect inelastic reflections in each other, all about that things are considered just kind of go on their paths, everything. Well, at the same time, they're all in orbits to each other. That's solving the many-body problem, and how they all gravitate together is like, I mean, they're all moving in their straight lines and the geodesy and the world lines all the time, and that's just instantaneously evaluated. And it's like, well, yeah, they're orbiting each other all the time, and so that is instantaneously evaluated. Whether it's unlinear at this point. So trying to figure that out is it gets involved with these kinds of things, but not so much more than these kinds of things. You know, this is kind of how it is. These are the ways of these things. So what I got to figuring out is this. So calculus, according to dimensional analysis and according to the formula of the derivative and the integral, it goes smoothly in these powers, because according to our power law in calculus, you can always just take something to the nth power and reduce it to the n to the thing to the n minus 1th power. That's its derivative. Form this back up the other way makes the antiderivative. So this is totally useful, and the most great mechanism of the dominoes falling down, or the water chain, or what is one of those things that has the little boxes that flip back and forth according to the ribbons that hold them together, but somehow they still say the same, you know. A connection of these things in a cascade as what carries on this thing, right? That's the most usual thing. So what I got thinking about was this, is that, okay, the change of velocity is dv dt. And then with regards to that being also about the change in momentum, see, momentum stays the same with that. It's like just mv's, so they're both just linear together, and mass is a constant. Up to relativistic dynamics and mass energy equivalency and stuff like that, it's a constant. So it comes up and down in the dimensional analysis, keeping that the same kind of thing, force equals mass times acceleration at the end. So the idea is that after kinetic energy, whether inertia has a defined thing, and it's not a constant, it's a running thing that comes up and goes down with these higher orders of acceleration. So this is about what I figured out about it so far. And then what I was wondering about is then for the derivation, because it's got to have a formula. You got to have a way to write the expression in the terms, in the infinite expression. It's got no highest order of the acceleration. It's infinite in the expression. how to change that instead of being just a regular power law, and that instead of having something that's either alternating or skipping, that kind of goes up in the power, or that it gets into the aerial terms. It expands in the order of that, helping to reflect that it's the inertia that comes into that must at once in the implicit fill out the power space, and with its that's inverse reciprocal being the root, having the root of that so that it still maintains a linear type of development, because it affects to reflect that Sisyphus pushing his rock up the mountain must always reach the top. Every day it falls back down, but that's for tomorrow, that the linear still must exist as a classical limit in the middle. And then the formula, the expression is to be that too, because everybody can add that up, right? Compared to that, it's like, well, it's just the sum of histories or the sum of potentials over the whole thing, which abstractly, of course, it is, but that's too big a formula to figure out these kinds of things. So the higher order derivatives and higher order anti-integrals, or pre-derivatives, or as you might want to put it, has been talked about in this descriptive differential dynamics, that we got integral equations, we got differential equations. Are they just each other's inverses and reciprocals? It's like, yeah, except that the one singularities on their side are all his multiplicities, and one singularities on their side are all his multiplicities. Not the same. In terms of their implicits, in terms of the setups, the ansatz, their quantities, what could derived algebraically. Where algebra and arithmetic and geometry all sit great in the middle about our integer lattice and all the real valued space. Whoa! Vis-a-vis these the openings and analysis for things like the complex numbers, like I'm modeling rotation in this space, I'm modeling screw arithmetic in this space, I'm modeling analyticity of this complex numbers in this space. I got a real funny formula called Euler's identity, and it just kind of picks those out a little bit, and it's really lucky. It's got a lot of luck to it. When it doesn't, it falls apart. Don't look at it crosswise. It just doesn't work anymore. Then for this harmonic theory, and that being the theory of potentials, it's like, how does the harmonic theory work? It's like, well, you can just kind of tap it around either side, and it forms this constructive and deconstructive interference. And then in terms of the entire thing, having like all together a constructive thing, well, that's for completions in these limits. So in the infinite limit and these continuum limits, these things are to add back up. In terms of what we're looking for is a derivation that's linear in the higher orders of calculus, integral calculus. And here about the idea that the dimensions as about this dimensionless resonator, I just put those two words together, even for the first time in my mind. That's what I'm thinking. Is the idea that then the powers go on and off and on and off and on and off and on and off, yet they still accumulate and come all the way back down together, so that it folds in and out the dimensional and dimensionless quantities. As they come down, the units stay coherent, because in a straight line, it doesn't fall off the ridge, or it's in the rut or on the ridge. These concepts. Meters per second, or seconds per meter. So you can see that this is the kind of idea that, without too much further ado, can get quite far afield. And at the same time, it's all entirely constrained by the bodies of definition in our descriptive definitional dynamics for these descriptive differential dynamics. Let's see what the books say. This is Lucretius on the nature of the universe. So about 50 BC, or 100, Lucretius lived, it says, in years 100 to 50 before Common Era, before Christ, BC. And he was a theorist. He was a great theorist and a pretty good scientist. And so he's got biological evolution, a theory of atomism. He's got a theory of light and images, or what he calls films. he's got atoms everywhere. So after the elementary and elemental, and the elements and the substances, Lucretius has some concepts that you wouldn't find again for 1,800 years that are usual and part of our, our lens into the theory and the history of things. The atoms rush in and out among one another on atomic trajectories, so that no one of them can be segregated nor its distinctive power isolated by intervening space. So this is usual idea of ultramundane corpuscles like gravity. What mode of combination they derive their powers. They coexist like the many properties of a single body. So Lucretius has this as his notion of the animus and the flux and these kinds of things associated with theory of the constituent bodies of an elementary and fundamental theory, these descriptive terms. So it is with men. He's a great study of the biological and mind and spirit. And then he kind of comprises those two things. He has a lot of mental stuff going on. The seat of guidance and control of life, the mind, what we often call the intellect. These are some who argue that the sentience of the mind is not lodged in any particular part, but is a vital condition of the body, what the Greeks call a harmony, which makes us live as sentient beings without having any locally determined mind. So Lucretius is just fantastic, really. He is, if you didn't know anything about science and you read Lucretius, you'd be way ahead. Since there can be no colors without light and the atoms do not merge into the light, it can be inferred that they are not. About darkness. Let us suppose you could say that something we often see, promptly transformed, the churning up of its matter and a reshuffling of atoms. So this just kind of reflects the, an idea that it's like, it's the sum of all these things, Because here we're looking for exactly the sort of thing that brings to our classical milieu something that works with what's called Einstein's bridge, which gets into exactly what's going on with inertia, because physics is an inertial system and a differential system according to general relativity, that it works out for the kinetics and kinematics, where we kind of have well-defined moments of inertia about the kinematics and the rotational, the changes in that with regards to how that is for moments and momentum vis-a-vis momentum, the property when you think of it linearly, and with the linear higher orders, the linear dimensioned unidimensional derivation in the integral calculus with respect to time, getting into these ideas of then what about the order of the derivative out and back in each time? How does it make for momentum to come through also linearly or not? That momentum gets this rest exchange momentum vis-a-vis inertia, which is that it's an inertial system overall. About energy and inertial energy and the energy involved with momentum and the exchange of momentum. All one inertial system, all one differential system, is what Einstein says relativity is. So, and then adding that back up, because for Einstein's bridge, then he says, hey, and also it has to be linear, so my model philosophers, model physicists can crunch it. The idea being to provide a dimensional analysis, non-standard, yet well-founded in a sense, ordinary, regular, rulio, still has to be, inferable and reasonable, sensible, fungible, and tractable, being the usual desiderata and requirements of the theory to arrive at these things. So Movements and Shapes of Atoms is book 2 of Lucretius. Anaxagoras. Even the smallest bodies will consist of an infinite number of parts. Infinite number of parts, since they can always be halved and their halves halved again without limits. So he's familiar with the Eleatics and this kind of thing. So he was a Roman, I guess. Devoted his life to the exposition of the studies of Epicurus. So if there's Plato versus Epicurus, Epicurus is the idea of sensualism and the phenomenological, and it's like I can see it if I can touch it. It's real. Vis-a-vis what is like what's real is in my mind. Can we grasp that? That it is. Plato says you must. This kind of thing. This is Polybius. So Polybius is kind of regarded as a historian. He was a Greek, and so he though lived in the Roman Empire, and he was considered one of the first universal historians that we still have a history of it. And so then he addresses the stories. It's got a great recount of the story of Rome and Hannibal and Carthage and their conflicts, and the story of Hannibal and Hannibal's victory is all about the Mediterranean basin and the development of Rome's constitution and Rome's and Italy's more largely unification, in a sense, of that. After we have the notions of the Athenian democracy, then we get into Roman democracy, or as regards to its constitution and the rule of law of Rome. And the idea was that this symbol was this axe, and then it has these 12 rods strapped around it, and that was basically the idea of one of these symbols that then was so represented for these ancient peoples who were largely schooled and that theorized in a notion of animism, and they had names for all kinds of motives to things that were unscientific, and yet at the same time express some reasoning, some inference. So Polybius is a great storyteller, and then he describes he was along on these campaigns and observed many and most of these things, and then he writes a history, and then also he criticizes some other authors of history for being fabricants. Anyways, I just have this there next to Lucretius. This is some of Aristotle. So Aristotle, this is by Richard McKeon, and so McKeon was an Aristotle scholar and a classical philologist, a study of words, a classicist. And anyways, he has here kind of an annotated Aristotle, harmonic theorems, arithmetical demonstration, and other sciences likewise possess each of them their own genera, so that if the demonstration is to pass from one sphere to another, the genus must be either absolutely or to some extent the same. So this reflects, that we have a dimensional analysis, and that so satisfies all else held constant. There's nothing else that varies. So these. If this is not so, transference is clearly impossible, because the extreme and the middle terms must be drawn from the same genus. Otherwise, as predicated, they will not be essential and will thus be accidents. That is why it cannot be proved by geometry that opposites fall under one science, or even that the product of two cubes is a cube. His examples are they're without our fuller dialectic of today. So this is part of posterior analytics. So Aristotle's basically got prior analytics, which is the usual idea of syllogism, and then posterior analytics, which is this greater discourse on deductive inference, principle of deductive inference, and all what we hold true as reasoning today. So Aristotle, he was Alexander the Great's tutor. And then after Alexander the Great died, then it wasn't, he didn't have much time after that in the world. But his books here survive today and are very well held up as among the most influential of all. The Humanities, to Philanthropia, the Bibliotheca of Photius, and the Lexicon of Suidas are handbooks of literature and history. The Syriac Christians, Muslim scholars, Judaism, Christianity, and Islam. The Middle Ages, shaped in 4 distinct and paradoxically related phases. So this is part of McKeon's introduction. He's a pretty famous guy. And there's not too much about physics here. It's on the soul. There's biology or the studies of animals, psychology, physics. Here's physics. He's got something about physics. Why? The principles which cause motion in a physical way are 2. Which one is not physical, as it has no principle of motion in itself. Of this kind is whatever causes movement, not being itself moved, such as that which is completely unchangeable, the primary reality, and the essence, that which is coming to be, i.e. the form, for this is the end, or that sake of which. Otherwise, you might have that as like that which we push against. The immovable object. When we are the immovable object, we are the lever. Vis-a-vis the mechanical advantage with a very simple direct formula given fulcrum, length, weight, and time. The application of force and the notions of the simple machines with their very direct and relevant and interpolated applications. Hence, since nature is for the sake of something, we must know this cause also. We must explain the why in all the senses of the term, namely that from this that will necessarily result from this either without qualification or in most cases that this must be so if that is to be so. So the conclusion presupposes the premises that this was the essence of the thing, and for because it is better thus, not without qualification, but with reference to the essential nature in each case. So this is part of his physics. It is the business of the physicist to know about them all. These causes, the idea being to reduce that to a sum of histories and a sum of potentials, or otherwise, that which rises must fall, or least action plus inverse, these kinds of things. Because otherwise, it does not have an explanation. For they cause motion not by possessing motion or a source of motion in themselves, but being themselves incapable of motion. These are the moments upon which these things kind of reflect. Then he gets into things that are destructible and things that are not destructible. Here we turn that and be deformable and non-deformable, compressible and incompressible in their models of their surfaces and the volumes in their bodies and the spaces, particularly. And then as with regard to fluid models, particularly in the open and closed, and the gas models in the open and closed, these systems and the conservation laws about the quantities and their units. So, higher order everything. Linear, classical, just being in the middle of a theory of some potentials, integral of some histories, projection as going forward according to the theory of some potentials. And he talks about science. It's clear that the knowledge of the things demonstrable cannot be acquired by perception, but by unless the term perception is applied to the possession of scientific knowledge through demonstration. Nevertheless, certain points do arise with regard to connections to be proved, which are referred for their explanation to a failure in sense perception. There are cases when an act of vision would terminate our inquiry, not because in seeing we should be knowing, but because we should have elicited the universal from seeing. If, for example, we saw the pores in the glass and light passing through, the reason of the kindling would be clear to us because we should at the same time see it in each instance and intuit that it must be so in all instances. Then he talks about syllogisms. All syllogisms cannot have the same basic truths. Yeah, I've been studying logic a bit. As from the previous talks, we got into that quite a bit. And the syllogism is kind of twisted today for the classical quasi-modal logic, which makes it so very, very readily computable. It makes it very tractable at the cost of some of its sense. It's an application among a greater field. Scientific knowledge. So physics, with regards to Aristotle, has much yet that I have not read this vis-a-vis motion and moment. But there is basically this reflection on the most usual mesoscale experiment of moving around from place to place, and one step at a time. Nicomachean ethics gets into ethics and morals. So after that is like, this was responsible and basically the handbook for all of civilization. Poetics. Let's see here. This is what I want to look at. So this is Feynman, Leighton, and Sands, their lecture notes in physics. So we looked at these somewhat before in descriptive differential dynamics, and a bit when from reading Einstein, and a bit when from reading about the path integral, which is part of this sum of histories. In the path integral, it's kind of like, well, yeah, this is the only way we can add up quantum mechanics, and it makes sense. Copyright 1965. Pretty good year. Science. So, introductory physics courses. So as you can tell, this discussion so far is really just very elementary and kind of introductory with regards to then all the different direct, immediate, and usually computed things which have to be kind of held up and put together to end up being able to add them all together and add up these things. Gets into lots of different configurations of the experiment. Here then, with regards to something like the Feynman path integral, it's like there's lots of energy, or that's the floor of the energy in the experiment. But all these diagrams just add up this way. They're configurations. So configuration and energy of experiment is just like the shape and scale parameters of distributions, and it means kind of what are the singular points, and then what are the inputs, the initial conditions. Probability waves, probability amplitudes, identical particles, spin one, the ammonia maser, the Hamiltonian matrix, the dependency of amplitudes of time. So this is mostly atomic physics. Forces, the classical limit. Let's see what it says about this. 7-4, 7-9. Where is this now? Forces, the classical limit. Suppose that we have a particle moving along and passing through a region where there is a potential that varies at right angles to the motion. So it'll be deflected. Otherwise, and this has the independence of the coordinates. Is like Galileo, he took a cannon and he just on a cliff. And so first of all, he just dropped a cannonball off the cliff. And it just falls in one direction, but is going this direction, that dimension, only 0, and then it just fell down. So he shot another cannonball, and so when he shot the cannonball, they both landed at the same time because they both just drop at the same time, is the idea. Vis-a-vis, if he would enable like the spinning or what can make for a space contraction and the gyroscopic effect, explains by the rifling of bullets and stuff, makes it go straighter. That these are the kinds of things that help reflect for Galileo's experiments, that they keep things simple. The one where he's got a heavier and a lighter object and drops them at the same time and they fall at the same time because the relation of the two masses according to the inverse square then of the force that accumulates, gets integrated over all that, is indistinguishable or negligible. Vis-a-vis some of the things that go on to the rest exchange momentum is like, well, when you imported it to the spinning and the spiral effect, wire spiral football goes farther. It's real. It does. So Feynman, he says, hey, we've shot we've accelerated some particles and we shot them down the track at slack. And then at the end, we got a magnet and we got a guy kind of waving it around. Classically, we would describe the situation as so. And if the particle is moving along the x direction, it enters a region where there's a potential that varies with y. So it varies, it's into like the inverse in this field, or the inverse square. It's not just a constant over the course of that range. The particle will get a transverse acceleration from the force F equals negative dv dy. If the force is present only in a limited region of width w, the force will act only for the time w over v. The particle will be given the transverse momentum p sub y equals f of w over v. The angle of deflection, d theta, is then d theta equals p over y over p equals f sub w equal, or excuse me, fw over pv, where p is the initial momentum. Using negative dv comma dy for f, we get d theta equals negative w over pv dv dy. So you see he's kind of added this back up and back over to just like, well, first of all, I'm just going to go from one to the other, and then for the reciprocal part, just bring it right back. Because I don't want to go out into higher orders of acceleration, because then the terms would either multiply out and get into the dimensional analysis, or I didn't have a way to keep these terms reciprocating and pulling back alternatingly so that they just come back and down the same line as linear. These are the ideas that I have for the stop derivative. So the stop derivative is the idea of just figuring, well, I just want the derivative to go up and down the power law and the positive powers, and then for the inverse powers to also get over the hump at the -1 to 0. So it's like it goes all the way down, bump out back, you know. And so to explain for the power series either way and the positive powers and the power series the other way and the negative powers, how something sweeps through all that kind of stuff, the stop derivative, because then it will help explain that we have acceleration and deceleration. This is another way to look at it. So the stop derivative is a thing. It's one of these ideas. But then this other idea of this dimensional resonance is this development that I hope to describe to you today. So Feynman has set this up. It is now up to us to see if our idea that the waves go as 7.20 will explain the same result. So 7.20 for non-relativistic situations has got Planck omega, and so this is for the classical behavior of the particle according to the electron physics equals W n plus p squared over 2m plus v. What about the physical phenomena? If there are several different energy states, what will we get? And he explains the amplitude for each state has the same additional factor, and then this gets into e to the negative I, or Euler's identity, and this whole setup. The framework, the setup, the dimensional analysis out in the complex plane and back, which is very well known. Over Planck, h bar vt over what it would have with v equals 0. This is just like a change in the zero of our energy scale. It produces an equal phase change in all amplitudes, but as we have seen before, this doesn't change any of the probabilities. All the physical phenomena are the same. Also, it has to stay right both ways. Yeah. Classical in the limit. So back to that's what he's talking about there. We'll explain the same result. We look at the same thing quantum mechanically, assuming that everything is on a very large scale compared with the wavelength of our probability amplitudes. So I'm not quite sure what that one entailed, very large scale. But it's about this local and global, and it's like our field is more than local, so it attenuates right away that it doesn't out through that. This kind of thing. In any small region, we can say that the amplitude varies as e to the negative I over Planck bar w plus p squared over 2m plus v, or from that minus vector p dot vector x. So the momentum and x is here. X is a position. Often you might see dp dt is like it could be mv, or it could be it's usually position, or is the idea. Displacement. P is often written for displacement for position. Here it is, as we've been talking about, we're having a difference between the length of the body and the displacement, even though they're in the same units, because they're related as about and around the algebraic derivations of dimensionally resonant quantities. Now, this is going to have to be clarified quite a bit, what that means, because I basically adopted from resonance theory that it's supposed to solve the wave problems in the harmonic, in the unlinear, out past the highly nonlinear. It's completions of the things. And for the dimensional, it's like the dimensional is, you can only have so many, it's before there's too many to keep track. But it goes through all of them. There's only 3 space. These kinds of things. It's a bookkeeping. It's all got to be bookkeeping to keep track of all these things and to cancel them away, so then we can have something that results out as sensible, fungible, and then tractable. These are the goals of this kind of thing. In any small region, can we give that this will also give rise to a deflection of the particle when v has a transverse gradient? We have sketched that the waves of probability amplitude will look like we have drawn a set of wave nodes, which you can think of as surfaces where the phase of the amplitude is 0. So then we have kind of have to recall the ideas of phase and what emits and doesn't emit phase. And so in this momentum phase momentum, and momentum phase is the idea of this alternating things. It associates with the idea of this alternating things in the powers, so that when you take these oscillating or alternating higher orders of acceleration in this dimensional resonance development, is that incorporates the notion of phase in it. So phase momentum and momentum phase. Great. Now 2 underdefined quantities together make it. This is kind of thing that is sort of immediately associated from relating, which then, if written correctly and just squared on down, made into a formula, both Einstein's and Feynman's model physicists will gladly eat it up, because it's sensible, fungible, and tractable, and particularly for them, fungible. They got computers for tractable, and they got philosophers for sensible. We have drawn a set of wave nodes. In every small region, the wavelength, the distance between successive nodes, where the wavelength is a constant, or it varies, but then the phase is as of about that, according to that it travels. lambda equals h over p, where p is related to v through w plus p squared over 2m plus v equals a constant, so that 720 is a constant. Somehow implicitly it's like this is kind of held implicit and constant in the region where v is larger, p is smaller, and the wavelength is longer. So the angle of the wave nodes gets changed as shown in the figure. To find the change in the angle. So really what this reminds me about is, and I was studying recently, was Cherenkov radiation. So what's Cherenkov radiation? It's like, well, light only goes so fast in a vacuum, and it's the maximum speed. And then light in a medium goes quite a bit slower. And in fact, you can find that some particles in the medium will go faster than light in the medium. So when they say nuclear particles are coming out of an accelerator, or even just out of nuclear reactions, about the weak and electroweak nuclear radioactivity, it makes Cherenkov booms. So like when you go past the speed of sound, it's called a sonic boom. And when you go Cherenkov radiation to Brehmsstrahlung, breaking radiation, is this. And so anyways, as it does, it's Huygens principle, radiating waves from radiating waves radiate, makes it so that it makes angles of these cones. And so these deflection angles kind of reflect on the idea of Cherenkov radiation that help make it so wide. Then this is to make a connected linear thing over the course, while the passage of something, and that its radiations are as about it, that these kind of formulas would be able to predict this to be like so, and to have the mechanism to explain and predict why it's so, and then under changes to be able to observe and make an arrangement for detection of falsification of changes that otherwise is just the average of these things. It's like, what does the theory predict? The theory predicts right down the middle. Well, what does it look like? It's like it's all over the place, but in the middle it's kind of like that. Well, that's a fact, for what it is. The wave number. This is the amount by which the phase on path B is ahead of the phase on path A as the wave leaves the strip. This is path here. But outside the strip, a phase advance of this amount corresponds to the wave node being ahead by the amount. So this is this resonance and this kind of thing. The re-wave, the re-flux, these kinds of things. So anyways, I guess that's where we kind of got to today. So about the first half was talking about meters per second and seconds per meter, and meters per second to infinity, and meters per seconds per meter per second, meters per seconds per meter, or meters per second times seconds per meter times meters per second times seconds per meter, making this dimensional resonance. That is about waves. Waves are generally the thoroughly understood and well-formulated milieu involving what they have for both particle models and resonance models, and it is the exchange of energy in open systems and physics. So that's what we got to today. And I suppose next is, well, we've been reading Despaignat. And so Despaignat is a physicist and he's a philosopher. And where we got was we were talking about the locality and the hidden variables of quantum mechanics, this particle wave duality, and the wave theory, the arithmetical paradox by Schrödinger. Essentially consists in that within the idealism in question, it is hard to discern what accounts for the intersubjective agreement between all these three I's, short of introducing the ad hoc notion of some universal I having in fact nothing but the name in common with that what the pronoun I refers to. Since the conception proposed here does not coincide with radical idealism, the difficulty in question is in it less acute. It cannot be claimed that it altogether vanishes for the impersonal character of the rule yielding probabilities of observation. The Born rule still looks somewhat enigmatic. However, it is less offensive. We have long been familiar with the idea that physical laws are universal, so we are hardly surprised in observing this universality extends even to those that are merely predictive of observations. So there's a big disconnect with quantum mechanics until it's continuum mechanics, and quantum mechanics is never wrong, and the idea is that it's a continuum mechanics again. It's like, well, how can that particle show up in the detector as if it were randomly through a wave, the front of a random wave? It's like, well, that wave is a constant. It's just infinitely going around it all the time. And so where it stops, nobody knows, is the idea. Round and round and round it goes. Where it stops, nobody knows. So this is the idea that makes for then this superclassical attachment. So the hidden variables of quantum theory make it so that then thusly it's possible to have a pretty simple reasoning explain that, as long as then that's figured out, and then how that doesn't violate causality, because that just makes for a state of things and this reflux of the things, and overall the superclassical model of the sum of history is sum of potentials. Not so bad. Well, I shall so hope you have a great day, and a great day, and that all is well with you and yours, I shall so hope. And then as with regards to the weather, let's see, the weather's enough that the sundial's spinning, so that means the energy output that's solar, that's arriving on Earth, is up. So good luck, and moment in motion. Around it goes.